गुड मॉर्निंग स्टूडेंट्स। मैं बिंदु डडवाल, लेक्चरर केमिस्ट्री, गवर्नमेंट सीनियर सेकेंडरी स्कूल कल्याड़ा से हर घर पाठशाला में आपका स्वागत करती हूँ। आज हम करेंगे केमिकल काइनेटिक्स से कुछ और इम्पॉर्टेंट क्वेश्चंस।
यूनिट्स ऑफ रेट ऑफ अ रिएक्शन इज, तो रेट ऑफ अ रिएक्शन होता है चेंज इन कंसंट्रेशन विद टाइम। कंसंट्रेशन की यूनिट्स होती हैं मोल्स पर लीटर और टाइम की यूनिट्स होती हैं सेकेंड। तो मोल पर लीटर डिवाइडेड बाय सेकेंड, units will be mole per liter per second. So option C, moles per liter per second, is the correct option.
Specific rate constant of a first order reaction depends on the temperature. Option D is the correct answer. It does not depend upon the concentration of reactant or product, and it does not depend upon time. It depends on the temperature. The rate constant of a reaction is 1.2 into 10 raised to power minus 5 mole raised to power minus 2 liter square second inverse. The order of reaction is, the value of K is 1.2 into 10 raised to power minus 5 mole raised to power minus 2 liter square second inverse. Now, units of K are represented as K is equal to 1 upon time into 1 upon concentration raised to power n minus 1. When this comes to the top, it becomes concentration raised to power 1 minus n and time raised to power minus 1. So, if we know that the units are mole raised to power minus 2, that means mole raised to power minus 2 will be the answer for 1 into 1 minus n. So 1 minus n is minus 2. So minus 2 on this side and n on this side, we get n is equal to 1 plus 2. That is 3. So the order of reaction is 3. So option D, 3 is the correct answer. The order of reaction is 3. Identify the order of reaction from the following rate constant. K is equal to 3.3 into 10 is to power minus 4 liter mole inverse second inverse. As we know that units of rate constant are represented as concentration 1 minus n into time raised to power minus 1, and the answer for mole is minus 1. So 1 minus n is equal to minus 1. N goes to this side and 1 to this side. So we get n is equal to 1 plus 1, n is equal to 2. So the reaction should be of second order. So option A, the reaction is of second order, is the correct answer. The half-life of a reaction is halved as the initial concentration of the reactant is doubled. The order of reaction is, to calculate the order of reaction, let us write down the equation for half-lives of reactions. In this numerical, we see that the concentration C2 is double of concentration C1. So C2 is equal to 2 C1, and half-life 2 is half of half-life 1. So T half-life 2 is T half upon 2, half of first half-life. Now the relation is T half 1 upon T half 2 is equal to C2 upon C1 raised to power n minus 1. So second T half is half of first T half, means we have T half 1 upon, instead of T half 2 we can write down T half 1 upon 2. So 2 comes up. Similarly, in place of C2 we can write 2C1 because it's double the original concentration, the whole raised to power n minus 1. This cancels, and what is left is 2 is equal to 2 raised to power n minus 1. So 1 is equal to n minus 1, or n is equal to 1 plus 1, that is 2. Option A, second order reaction. The reaction is of second order is the correct answer. The units of rate constant and rate of reaction are identical for a zero order reaction. Option A is the correct answer. This is because units for rate constant for zero order reaction are mole, liter inverse, second inverse, and units for rate of a reaction are also mole, liter inverse, second inverse. So the units of rate constant and rate of reaction are identical for option A, zero order reaction. The radioactive decay follows first order kinetics. Option B is the correct answer. Radioactive decay follows first order kinetics. Which one of the following does not influence the reaction rates? Nature of reactants will influence the reaction rate. Concentration of reactants will influence, because more the concentration, more will be the rate of reaction. Temperature also increases the rate of reaction. Option D, molecularity of the reaction does not influence the reaction rate. So D, molecularity is the correct answer. A catalyst lowers the activation energy of the forward reaction by 10 kilojoules per mole. What effect it has on the activation energy of the backward reaction? So the backward reaction activation energy also decreases by 10 kilojoules per mole. We can see in this diagram that the the pathway for catalyzed reaction decreases the activation of forward direction reaction by this much amount. Similarly, for backward reaction also, the catalyzed reaction will decrease the activation energy for backward reaction by the same amount. So the decrease in activation energy for forward as well as for backward reaction is same. If the activation energy for forward reaction decreases by 10 kilojoules per mole, that for backward reaction also decreases by 10 kilojoules per mole. So option C, decreases by 10 kilojoules per mole, is the correct answer. The time taken for 99.9% of a first order reaction to complete is approximately. To find out the answers, let us solve the numerical. Time taken for 99.9% completion of a reaction will be 2.303 upon K log of A, that is 100, upon A minus X, that is 100 minus 99.9, it is 0.1. So this becomes T 99.9 is equal to 2.303 upon K log 0.1. 10 goes up, so we get log 1000. So for half life T half, that is for 50% of the reaction to complete, T half will be 2.303 upon K log 100 upon 50%. Log 100 upon 50 is log 2. So dividing this by this, we get time taken for 99% completion upon time taken for half life is equal to 2.303 upon K log 1000 upon 2.303 upon K log 2. This cancels out. We get T 99.9% completion upon T half is equal to log 1000 is 3 and log 2 is 0.3 approximately. So cancelling, we get 10. So T 99.9%, time taken for 99.9% completion is equal to 10 times T half. So option B is the correct answer. Does the rate of reaction become equal to specific reaction rate? As we know, the rate law expression states that rate is equal to K into concentration of a reactant raised to power n, the order of reaction. So in order that this should become equal to this term should be 1. And if concentration is 1, then anything raised to power is also 1. So the specific reaction rate will be equal to rate of reaction when concentration of reactant is unity. The kinetics of the reaction 2NO plus H2 gives N2 plus 2H2O is explained by the following two steps. 2NO plus H2 forms N2 plus H2O2. H2O2 plus H2 gives 2H2O. Fast. What is the predicted rate law? As we know that the rate of reaction depends upon the slowest step, therefore the rate will depend upon the reactants appearing in the slow step. So rate equation will be rate is equal to K, rate constant, into concentration of NO raised to power 2, the stoichiometric coefficient appearing here, into H2 raised to power 1, because 1 is the stoichiometric coefficient here. So this is the predicted rate law. Derive integrated rate equation for a zero order reaction. For a zero order reaction, we know that rate equation is rate is equal to K into concentration of reactant raised to power 0. So rate is also given by rate is equal to minus d of A upon dt is equal to K into A raised to power 0. But A raised to power 0 is 1, and taking dt to this side, we get rate is equal to minus differential of A into k dt, or differential of A is equal to minus k dt. Now to find out the integrated rate equation, let us do the integration of the equation. So we get integral of d of A is equal to minus k into integral of dt. So this comes out to be A is equal to minus k t plus I. To find out the value of I, let us consider time t is equal to 0 when the concentration is initial concentration, or A naught. So at time t is equal to 0, A becomes A naught is equal to minus K into T becomes 0, and we have I. So I is equal to, because this term is 0, A naught. So when I is equal to A naught, we can substitute the value of I in this equation. So what we get is A is equal to minus KT plus A naught, or taking A to this side, we get A to this side and KT to other side, we get KT is equal to A naught minus A, or K is equal to A naught minus A upon T. So this is the integrated rate equation for a zero order reaction. So next question is, give differences between rate of reaction and reaction rate constant. So rate of reaction is the rate of decrease of concentrations of reactants or rate of increase of concentrations of products per unit time, whereas reaction rate constant is the constant of proportionality in the rate law equation and is defined as the reaction rate when the concentrations of each reactant is unity. The rate of reaction at any particular instant of time depends upon molar concentration of reactants at that instant of time, whereas the rate constant is independent of the molar concentrations of reactants and is constant at a particular temperature. The units of rate of reaction are always moles per liter per time, whereas the units of rate constant depend upon the order of reaction. For zero order reaction, rate constant units will be mole per liter per second. For first order reaction, it will be second inverse, and so on. What is half-life period of a reaction? Derive an expression for half-life period of zero order reaction. Half-life period of a reaction is defined as the time during which the concentration of a reactant is reduced to half of its initial concentration. Let us derive the expression for half-life period for zero order reaction. For a zero order reaction where the reactant A changes to products, we know that the rate constant K is equal to A naught minus A upon T. Now, T half is the half-life period. It is the time when the concentration of is A naught is reduced to half. So that means at time t half, A will become A naught upon 2. So we get K is equal to A naught minus A naught upon 2 upon T is T half at this time. So taking T half to upper side, we get T half is equal to A naught minus A naught upon 2 will become A naught upon 2. 1 minus half is half. So A naught upon 2 into K. So this is the expression for half-life period of a zero order reaction. So draw graphs to show variation of T half, the half-life period, with initial concentration A naught for zero order and first order reactions. So the T half versus A naught graph for a zero order reaction shows that T half is directly proportional to initial concentration and graph is a straight line. Whereas for a first order reaction, the T half value, it shows that it is independent of the initial concentration, and the graph is a horizontal line parallel to the x axis, a naught axis. So these are the two graphs for zero order and first order reactions. Define pseudo-molecular reactions and rate law. The reactions which are not truly of first order but under certain conditions become reactions of first order are called pseudo first order reactions. For example, hydrolysis of ethyl acetate is an example of pseudo first order reaction. Rate law may be defined as the mathematical expression which denotes the rate of a reaction in terms of molar concentration of reactants, with each term raised to some power which may or may not be the same as the stoichiometric coefficient of the reacting species in a balanced chemical equation. It gives the experimentally observed dependence of rate on the concentration of reactants. Calculate the order of reaction for which rate law expression is rate is equal to K into concentration of A raised to power 1 into concentration of B raised to power 2. So the order of reaction will be the sum of the stoichiometric coefficients as appearing in the rate law expression, that is 1 plus 2 is equal to 3. So order of reaction will be 3. The rate constant for a first order reaction is 2-minute inverse. Find out the value of its half-life period. Half-life is equal to 0.693 upon K, as K is 2-minute inverse, so it is 0.693 upon 2 is equal to 0.3465 minutes. After 5 half-life periods for a first order reaction, what fraction of reactant remains? According to the formula, A upon A naught is equal to 1 by 2 raised to power n half-lives. Because number of half-lives given are 5, so putting the values we get A upon A naught is equal to half raised to power 5. That is, fraction of sample is equal to 1 by 32. In order of reaction. So order of reaction is defined as the sum of the exponents to which the terms must be raised in the rate equation to express the observed rate of a reaction. For rate law expression, rate is equal to K into A raised to power 2 into B raised to power 1. Order is equal to 2 plus 1 is equal to 3. Give an example of zero order reaction. So H2 plus Cl2 in the presence of sunlight gives 2HCl is an example of zero order reaction, and 2 ammonia in presence of platinum at 1130 Kelvin give nitrogen plus hydrogen is also an example of zero order reaction. Give an example of reactions of first order. So 2N2O5 decomposed to give 4NO2 and O2 is an example of first order reaction. Similarly, H2O2 gives water plus half oxygen is also a first order reaction. Give examples of reactions of second order. So 2NO2 plus F2 gives 2NO2F is a second order reaction. 2HI decomposed to give H2 plus I2 is also a second order reaction. Dear students, this is all in today's video. Practice the topics that we did today. Solve numericals. Keep watching and keep learning. Stay safe and healthy. Thanks for watching. Have a nice day. Bye-bye.